Now, we saw that how hydrazine on reaction with our D-glucose was giving osazone. So let us now see the mechanism which follows in that reaction. So if we start with D-glucose, so let us start with D-glucose now. What is D-glucose? It is nothing but C double bond OH group attached at the top with CH2OH group at the bottom, and we have OH on the left hand side of the second carbon and OH on the right hand side of the rest of the carbons. We have got this, and this is nothing but D-glucose. Okay, so we have to start from D-glucose and we have to proceed. So we just learned that D-glucose on reaction with 3 moles of hydrazine gives us the required osazone. So now let us take 1 mole of that hydrazine and react with this D-glucose. So we have got hydrazine as NH2, NH and PH. So we all know that nitrogen has a lone pair of electron, and these lone pair of electron will attack our carbonyl carbon here, and what are we going to get here is we're going to get a C accompanied with a double bond N and NH and a phenyl group, okay, and a hydrogen. So you can clearly see that now why that happened is because this H2 of this N and this oxygen of this C double bond O, that is the carbonyl group, is lost as water. So what is being lost? We are removing a water molecule from this, and then this double bond is getting attached to this hydrazine. So now what are we left with? The same structure of D-glucose remains at the rest of the valencies of carbon, chiral carbon. So now we have got the exact same structure. The only difference is that now we have the C double bond not attached to a O group but rather attached to this hydrazine, the left part which is left of hydrazine. Now here we see that we consumed 1 mole of hydrazine over here. We are still left with 2 moles of hydrazine which we are going to use in the further reactions. So now what this second part, the second molecule does is it is going to tautomerize. Now, tautomerize into what? So, tautomerize is basically when we are shifting a H plus, that is a proton, from one part of the compound to another. And when this happens, a shifting of double bond also occurs. So, we are going to just mark all of the atoms with numbers. So, let us just call this nitrogen 1, the carbon second, this carbon over here, the third one. And now let us proceed. So, what are we going to get is this particular H over here is being lost from this side, and this double bond is also being shifted. So where are they going to be shifting? Let us just observe this now. So what we're going to get here is we'll get a C. This first carbon that we just drew is the third one, and this is attached now to a double bond. So the double bond is being shifted. It was previously at 1 and 2 position, and now it is getting attached at the second and the third carbon. These were the second and the third carbon, and we're getting a double bond. This hydrogen, which was originally at third, the atom, the carbon which we marked third, now moves to this position. Which position? Now this particular hydrogen over here is accompanying this nitrogen, and now what we get is something like this. So what we're gonna get is we're gonna get a nitrogen along with the hydrogen, that is the proton which moved during tautomerization, and now we have NH and we have pH. So we see that now we have got the same compound, but the position of the protons and the electrons have shifted, and this is what is tautomerization. The rest of the molecule looks exactly the same again. This here had an OH group attached. This particular OH, it remains in its position, intact in its position, and now the rest of the molecule will follow suit. and it will be the atoms will remain intact in their places. So the rest of the atoms are where they were before. So now we've got this molecule over here, and now what we're going to do is we're going to shift the bonds a little here and there, and what we're going to do is that this particular OH bond over here, this is gonna break. And when this breaks, what is gonna happen is this OH, the bond between O and H, is gonna shift to this side, accompanied by a shifting of this double bond between C and C. And this double bond over here shifts to this position, and this part of the molecule is detached. So what are we trying to say here? This particular bond is breaking, then accompanied by shifting of this particular double bond, and then the breaking of this particular part from the whole molecule. So now what we get is, I'm going to depict this. The next step here in this particular region, I'm coming down. So now, if I carefully see this particular compound, what is going to happen now? Now, first let us see which part is getting detached from the whole molecule. So now we have decided that this particular NH, PH is getting detached from the molecule. Also, this hydrogen of this O, which is left now, will get itself attached to this NHPH and lead to a side product, which is now we're left with PH, the phenyl, and NH from this particular region, and then a hydrogen from this OH, we're getting a hydrogen. So we are left now with PHNH2. Now, but the main part we're concerned with is the rest of the portion that is left. And what is left is, if we carefully observe, what are we left with? We're left with, let us see, we're left with a carbon here, which is attached to a carbon but not in double bond now, because the double bond is being shifted to this position, and this is attached to N and H. Okay. Okay. Now the hydrogen remains intact. It is not moving anywhere. As for the rest of the compound, this, when the H leaves, only the O remains and a double bond, and the rest of the molecule looks exactly the same. So we're going to draw it as it was before. As it was before. So now we are left with this particular structure over here. In this particular structure, we can clearly see that we have got a C double bond O and a C double bond NH. Now what is going to happen with these two double bond is that we are going to react these two double bonds with our 2 moles of hydrogen which were initially provided to us. So now we have NH2, NH and pH, that is 1 mole of hydrogen over here, and this another double bond will get another mole of hydrogen. So we are having 2 moles of hydrogen over here. So now we can clearly see that we have used all the moles of hydrogen which were provided to us, that is 3 moles of hydrogen. And now what is going to happen is that this particular C double bond is going to get attached to this hydrogen, and how it is going to do that? Let us see that also. So what are we left with? Let us see, we have got C over here and another C accompanying it, and we've got a double bond and a double bond over here. So now let us see what is gonna be coming next to this double bond. We have an N, that is a nitrogen, accompanied by an NH group and a pH group. Okay. So what did this molecule lose? We have got a nitrogen, we have got an NH and a pH. So we have all these groups with us. The left part is the part which is not here is a hydrogen and an NH2. So we can clearly see that we'll have an NH3 which will be a side product over here. Now in the second C double bond, we are going to attach same N, NH and pH. And this particular one, you can clearly see that this oxygen is removed and this H2 is removed, and now therefore we are getting a H2O as a side product in this one. Okay, the rest of the molecule remains exactly the same. That is HOH. We have HOH, OH, and CH2OH. So now this product, that is the end product which we got here, this is nothing but osazone. So this is the mechanism of getting osazone from D-glucose, which we initially had over here. We had D-glucose and now we got an osazone. So this is the mechanism of, just write the mechanism. So this whole was the mechanism of obtaining osazone from D-glucose. And what did we use here? We used phenyl hydrazine over here. The three modes of phenyl hydrazine which can be seen are this particular one, second mole is over here, and the third mole which we used in the first step. So this is how we get osazone when we react phenyl hydrazine, 3 moles of phenyl hydrazine with D-glucose, and this is the mechanism. So now what we initially wrote here was that D-glucose was giving us an osazone, and now we have seen how we get this osazone from this D-glucose when it reacts with 3 moles of phenyl hydrazine. So this is the mechanism which we have achieved after reacting 3 moles of phenyl hydrazine with D-glucose.